Okay, now we're going to look at a special case here. If we're trying to find the limits of some exponential functions. First, we're going to look at when we have the graph, which we should be fine with, but it's more about when we don't have the graph, how are we going to find these limits, okay? So first, we're going to start here when we have the graph of this. So we want to find the limit as x approaches negative infinity on this graph. Oh, and by the way, it's an exponential function because the x is in the exponent. Remember that this 2/3 is called your base. And when the x is in the exponent, we're going to look at how we can find these limits when we don't have the graph. All right, so as x approaches negative infinity means we're going all the way left. What height are we approaching? The answer is infinity. It's shooting up unbounded. As x approaches infinity, so as we go all the way right, we are approaching the horizontal asymptote of -2. So notice that on one side we have unbounded growth, and on the other side we have a bounded decay. It's bounded by the asymptote. I don't really want to call this growth because we're moving left here, so it's not really growth. But we can just say on one side it's going up to infinity, on the other side it's approaching the asymptote. Okay, let's look at this guy. This is now with a base of 3/2. It's exponential because the x is in the exponent. The limit as x approaches negative infinity is approaching that asymptote of -2. Right, we're here on the curve. The height is approaching -2. And as x approaches infinity, we're here on the curve. It's going up unbounded up to infinity. This guy, when my base is 1/2, if we look at as x approaches negative infinity, we are unbounded going downwards, so that limit is negative infinity because it's going to a height of negative infinity. It's unbounded. And as we approach infinity to do the right-hand behavior, we're approaching the horizontal asymptote of -1. Here, when my b is 1/2, we're looking at the left side as we go all the way left. We're approaching a horizontal asymptote of 2. And as x approaches infinity, we are approaching, we are unbounded going downwards to a height of negative infinity. So what's interesting to note here is when we do end limits at the ends, at infinity or negative infinity, these infinite limits, or I should say limits at infinity, right? For an exponential function, there's two options that happen. It either approaches the horizontal asymptote, which in this case was -2. In this case it was -1. In this case it was 2. Or it approaches infinity or negative infinity. So in order to determine a limit as x approaches negative infinity or infinity, that's the key for an exponential function. You have to determine what the graph will look like. That's how we're going to think about it. So when we see it without the graph, we have to picture the graph, okay? The three possible results for this would be negative infinity, infinity on the unbounded side of your exponential, or the answer is going to be whatever the horizontal asymptote is, if it's on the side where it's bounded. All right, we're going to sort of, okay, well, we can talk about this. It's growth if b is larger than 1. I'm going to say, but we have to consider any reflections. It's decay if our b is less than 1, and our b can't be negative, so I'm going to just say it also has to be bigger than 0. That's decay, but again, we have to consider reflections. This is how I want to think about it for now, if we want to decide if it's growth or decay, because we have to start looking at these and know kind of what the graph is doing. All right, so let's look at, whoops, I'm sorry. That was calculator camp. Let's look at the graph of 2 to the x. It's growth. From left to right, it's going up, which means the more important thing is you have to know what side is bounded and what side is unbounded. So when b is bigger than 1, the unbounded side will be on the right. It's going to grow up to infinity. And on the left side, it's going to approach 0 because the asymptote is at 0. Okay? What happens if we put a reflection in there, though? It's going to affect it. How do I reflect? Well, one way is if I throw in a negative. That will reflect it, what you just saw. Reflect it vertically because it's affecting the y value, essentially. Okay? So when that happens, we have to now take that into account because what happened to our limits now? Well, the left-handed limit is still approaching, as you go to negative infinity, it's still approaching the asymptote, 0. But on the right side now, instead of going up to infinity, it's going down to infinity. All right? So we have to consider that reflection. What happens if I reflect it in the other direction? That's if I negate the x up top. You see what happened there? It reflected it horizontally. That's going to change our end behavior now. If I turn these off, the originals for a second, you can see now that the end behavior is now unbounded on the left side and bounded on the right side. So you got to watch out for that reflection. So you have to know what the negative does. The negative on the exponent reflects it horizontally, and that's because x is horizontal. A reflection, a negative on the y value. So I wanted to show you the original. A negative on the y value, not on the x, which means we just basically put it in front here. It's affecting the y. That's going to reflect it vertically because the y goes vertical. And that's going to change our end behavior. What happens if I reflect both of them? Okay, it's growth again, but now the right side is bounded and the left side is unbounded. So we have to kind of know that that had two reflections. Okay, so where did that come from? Well, here was my original. And then if I reflect it once, I'll reflect it horizontally first. Right, so how do we get to that double reflection? Let's take a look at it. Here's my original. I reflect it over horizontally, I get the green graph, and then when I reflect it the second time, I end up there. So you got to be able to picture those reflections. The other thing that's going to matter is if you shift the graph up or down, it's going to move the asymptote. So I'm going to turn these off for a second and look at our original. How do you shift the graph up or down? If I add a constant, that's going to change our asymptote. It's now 3, which we know changes our end behavior. So you got to watch out for that as well when we're doing these. So it's about reflections and any vertical shifts. A horizontal shift means nothing in terms of the end behavior for the limit. If I shift it, whoops, I was supposed to be in the exponent there. If I shift it, why won't it let me do that? Maybe I have to put it in parentheses. Okay, here we go. If I shift it left 3, it doesn't affect my end behavior of, say, my original function. Let me show you the original. If I get rid of my negatives here. Okay, it shifted it left, but the end behavior is still the same. So we don't care about anything that it's doing to the x in terms of adding or subtracting. We do care about the reflections, all right? So let's go about this. Let's tackle this. So determine the limits of each of the following exponential functions. First of all, I have to note that we're talking about end behavior on all of these. This is the only time you have to do this. Exponential functions are continuous everywhere else. So when we get to these two down here, these are just direct substitution. Direct sub, I'll just say. Okay? So those ones, this does not apply to. Let's go back up here. So when we want to find this limit as x approaches infinity, we have to notice that, oh, the x is in the exponent. This is an exponential. I got to think about the graph. So the first thing you ask yourself is it growth or decay? Well, this one is decay to start with. So I'm going to start by drawing my graph as a decay instead of a growth. You have to kind of know that. And then we have to consider reflections. Well, there's no reflection because there's no, I should say, vertical reflection because there's no negative sign out front. This negative sign does give me a horizontal reflection, which now spins it this way. This minus 1 is going to shift it left or right or something, but I don't care about that for end behavior. So I could ignore that. Who cares about that guy? The minus 2 I do care about. It shifts everything down 2, and we're going to do that after our reflections. So now my asymptote's down here at -2, and we're going to do that after our reflections. So now, after I perform all of that, there's my graph. Now I can answer this question. As x goes to infinity, so I'm going to the right, as I move all the way right, I have that unbounded growth up to infinity. So that's that answer. That's the thought process you have to go through to solve some of these. Let's do another one. The ones that I skip, you can kind of do on your own. Here's one, I'm going to think of it like this. B is above 1, so that means I start off with growth. This one, B is less than 1, so I start off with decay. Now I've got to consider reflections. I'm going to do number 4. Start off with my growth. I reflect it, that means I reflect it vertically, so now it's this. This negative sign means I now reflect it horizontally, so now it's this. I don't care about this. Shifting left or right is not going to affect my end behavior limit. +2 shifts it up 2. So I bring up my asymptote up 2. There's my graph. The limit as x approaches infinity means I'm going as far right as possible. It's that bounded approach on 2. So this is going to be 2. I want you to try it for the rest of these. Number 2, number 3, number 5, number 6. You're going to try that on your own, and we'll talk about it in class. There is a way to do this through numerical analysis or some number sense, and we can talk about that in class as well. You don't have to think about the graph. We are going to do one of these direct substitution ones. Please note that when you're trying to find, we know it's exponential because the x is in the exponent, but when you're trying to find it at any other x value, the graph is continuous everywhere on the exponential graph, so we can do direct substitution. So I'm just going to say f of 3 is equal to 2, e to the 2 minus 3 plus 2, so I'm going to get e to the -1 plus 2. I can call that 1 over e plus 2. If you want to get a common denominator and keep going, you could call it 2e plus, what am I getting? Sorry, I'm skipping a step here. I'm getting a little confused. I want to get my common denominator of e, so that would be 1 over e plus 2e over e. So I can get 1 plus 2e all over e. You can try number 8.